Okay, so today we're going to continue on arrays, and as was asked right beforehand, your midterm is going to cover everything up from day one up to and including arrays. So we're pretty much going to be covering arrays up until spring break. After the arrays, but then also tooling with arrays. So in other words, we're going to be looking at GDB, which is a debugger, and also Valgrind, which is a dynamic analysis tool. Basically, we just needed to get to a point where we could use these tools in a meaningful way rather than introducing them earlier on. All right? So let's remind ourselves what we were talking about a little bit. Remember that we have arrays. Arrays are zero index because of how memory works. The first element is at index 0, the second element is at index 1, et cetera, et cetera. And if you have 9 elements, then your last one is going to be at 9 minus 1 at index 8. Okay? Just make sure that this works. Remember that we are online, so if you have any questions, go ahead and post to Piazza or to the YouTube live stream here. To continue, remember that we started out with static arrays, and we immediately saw the flaw with static arrays, that they're allocated on the stack, and the stack is limited. Even on, say, this Ubuntu system over here, I think it was what, 4 megs or 8 megs or something like 8 megs? Okay. Whatever it was, that's insanely small. So what we did is we moved on to dynamic arrays. Dynamic arrays allow you to allocate space on the heap, which is much larger but less organized. And so you do have to have this memory management for yourself. You have to make sure that you're keeping track of the size of the array. You're going to have to make sure that you're keeping track of the pointer to the array so you don't lose access to it, right? And you ultimately allocate a chunk of memory using malloc. And remember, there's only one malloc. You can use malloc for integers, you can use malloc for doubles, you can use malloc for chars, whatever. Why? Because you just simply tell malloc how many bytes you want. If you want 1 million integers, then you need 1 million times the number of bytes that an integer takes. And how do we determine whether or not how many bytes an integer takes? It's size of int, or size of double, or whatever you're trying to allocate. Then you typecast it, all right, and as an int pointer or a double pointer because it returns this generic void pointer. And then you can start using it like a regular old array. Right? Malloc only returns a generic void pointer because otherwise you need a malloc for doubles, a malloc for integers, a malloc for chars, ... Anything that you would want to do in the future, you'd have to have a new malloc for it. You would be reinventing the wheel on all of this stuff. Okay? All right, so let's go into a little bit more details here, or miscellaneous details, I should say. If malloc fails, what do you think happens? For any reason, right? For example, you've exceeded the maximum amount of memory that your process is allowed, or you've exceeded the amount of memory that's on the entire planet, or something like that, right? You've asked for an insane amount of memory. If it fails for any reason, it returns null. Why? That's the only thing it can return. Here's the signature. Does it return an error code? An integer error code? 0, everything was fine. 1, something happened? No. Because it returns a pointer to the chunk of memory that it allocates for you. The only way that it can communicate back to the calling function that the allocation failed is by giving you a flag value, in this case null, to indicate, nope, I wasn't able to do that for you. Okay? So if it fails for any reason, it returns null, and you can check for that. Okay? After allocation, you can treat the array like a regular old array, right? Indexing from 0 up to n minus 1, where n is the size of the array, right? Attempts to access memory outside that array are undefined behavior, right? It could result in anything. It may, and I emphasize may, result in a seg fault, right? It may do nothing, right? It may simply corrupt your own memory. When we did this with static arrays, what happened? Because they were on the stack, what was the message we got from the good operating system? On the stack?
Crash.
It smashed the stack, right? SS, right? Smash the stack, right? It's an alliteration there. Stack smashing event. Here, however, it might end up just corrupting your own memory. Okay, well, I gave you that chunk of memory. You can do whatever you want with it, including corrupting it. Right? It may do nothing. It may not end up as any. It might not manifest itself at all. It may result in a segmentation fault. It completely depends on how the underlying memory works. And I set this up. I'm going to go ahead and cut and paste this and save it and come back to it. Let's go ahead and take a look at it. So as a review, how do I create enough memory for, say, 10 integers? I'm going to keep it small. What do I need to point to that array? I need an integer pointer. Right? And what function do I call again? To allocate memory, or memory allocation, malloc, right? And how much memory do you want now? Size of int, because that's the number of bytes that an integer takes, right? Times n, the number of integers that you want, right? If I just left it like this, how many integers would I be allocating? 1, right? There is such thing as an array of size 1. We call that a regular old variable, right? There is an array of size 0, by the way. You can do that. It'll point to a memory location, and then nothing has been allocated for you. A valid memory location, it's not null because it's a valid memory location, but it is empty, right? You can do that, but it's kind of useless. So n, there we go. What else do I do here? You cast it as an integer pointer to match the type of pointer over here, okay? It does return a pointer, but what kind of pointer? Man, malloc. Oh, okay, fine. Malloc. Well, I've got its signature over here. What kind of integer? What kind of pointer does it return? A void pointer. What is a void pointer? It's a nothing pointer? No. Yet another instance in which we use a nothing keyword to mean something other than 0, right? So we've got 0, which is nothing. We've got the null terminating character in strings that we'll talk about later. We've got void, it returns nothing. Void pointer, it doesn't return a nothing pointer. It returns a valid memory address. It's just that this is called type erasure. We've erased the type. Is it an integer pointer? No. Is it a double pointer? We've erased that type. It is a pointer, period. It is a raw memory address. And because of that, we want to typecast it to force it to become an integer pointer, okay? And if you're interested in that debate that I was talking about on Monday, it's in the book, or at least I've got a reference in the citations to the debate on whether or not you should do this. And again, I'm going to tell you that you should because it makes your code portable over to C++. Right? Once you've got this, then you can go ahead and do whatever you want with it. Array of 0 is equal to 42. Array of n-1, the last one, is equal to 101. Right? And if you want to go ahead and start accessing memory that may or may not even exist or belong to you, you can do that. Right? 32. And a sub 11 is equal to 99. Right? There we go. Printf, first, last is %d, and the line, a sub 0, and a sub 0, and a sub 1. Or, sorry, 9. Or n-1, I'll go like that. Okay? CS1, lecture, GCC, demo. Oops. It's not A, it is ARR, 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 and AR. There we go. No compiler warnings. Let me go ahead and make sure that I've got all of those compiler warnings on there, right? Unlike static arrays where it can probably detect that you're going outside the bounds of the array, warning, no warnings here because it can't detect whether or not you're going out of the bounds of the memory because it hasn't even been allocated yet, right? Now, if I run this, what is your prediction? I'm trying to access something that doesn't belong to me necessarily, but I'm trying to access it on the heap. Ooh, excellent, corrupted top size, right? So it's probably complaining about this line right here. Let's go ahead and get rid of it, okay? And if I run this again, hopefully a good operating system will probably detect this, but, oh, excellent, wow, it is really sophisticated. So if I go even 1 or 2 outside the bounds, in fact, I could go just 1 outside the bounds. I don't know, could I get away with this? Sorry, 10, there we go. This is really good. Oh, wow. It is detecting everything, right? That is nice. Usually, this is all a very nice compiler and a very nice system doing this for me, right? If I took this over to your Windows system that didn't care about even a stack smashing event yet on Monday, right? I would potentially get completely different behavior. And the reason is because of how memory works. If you only ask for 10 integers, how many bytes does an integer take? 4. So you're only asking for 40 bytes, right? That's small chump change to a computer, right? It's not going to allocate exactly 40 bytes to you. It is going to allocate some sort of page to you, right? A page of memory. Pages are typically, say, 1K, 2K, 5K, or 4K, or something like that. Kilobytes is what I'm talking about. And it's going to, I'm going to allocate enough pages to fit the memory that you wanted. There might be a little bit left over. Right? It's not going to waste its efforts by allocating exactly as much space. It's just going to give you this entire page, and all right, you deal with it. Right? If you access anything within that page, that entire page belongs to your program. So if you only have 10 integers here, but you have an entire page to work with, you're only corrupting your own memory. Right? That's on you. Right? And the operating system generally doesn't care about that. This one does, apparently. But some other different operating systems will not even care. Right? Only when you try to access memory that doesn't belong to you, now it'll start carrying. If you try to access memory that belongs to another program that has passwords stored in memory, right? That would be a very, very bad situation if you were allowed to do that. And so that's why the operating system detects it and says no, and segmentation fault usually. Okay? But otherwise, wow, I'm really impressed by this. I think that this is Ubuntu, uname. Well, okay, it's just saying Linux, but I believe that it's Ubuntu Linux here. Right? All right, questions so far? Yeah, go ahead.
I tried to compile that, and I kind of just copied your code here, and I got a bunch of errors, and it says, for some reason it doesn't like my malloc function, I think.
Have you included the standard library? That's where it's located.
Yes.
Huh, what is it saying?
Expected comma or semicolon before int, and I was missing a semicolon at first, but then I recompiled it, and it still...
It's probably just a syntax error. I can take a look at it later, but... maybe there's a typecast or a missing parenthesis there somewhere or something. But anyway, so it may do anything. That's what undefined behavior is. In fact, I forget what it was called. There's a malicious C operating system for undefined behavior. I forget what it was called. It's like System 32 or something like that. Darn it. Anyway, there was somebody created a malicious compiler, a malicious system, not a malicious system, a completely C-compliant system that in the event of any undefined behavior, it would immediately say, wipe out the hard drive, right? So that instead of manifesting itself as a segmentation fault, it would go ahead and delete all the files, right? Or something like that. It's because it's to drive home the point of undefined behavior is undefined behavior, right? Do not do that, right?
So technically speaking, it was still compliant.
Yeah, it'd be completely compliant. Right, it's maliciously compliant, right? There's an entire subreddit like that, malicious compliance. Right? I'm going to go ahead and follow your stupid rules, but I'm going to do it maliciously so that it comes back out on you, right? So undefined behavior is undefined behavior. You cannot read anything into it other than something bad happened, right? Now, hopefully, it will not delete the hard drive or anything like that. But there are other operating systems that is a feature, right? So high security systems, for example, if you're if you've got secrets on your hard drive or whatever, right? You can go ahead and have a sham password that say, okay, yes, I relent. Here, my password is 1234, and that password triggers a bunch of other programs to just wipe out the hard drive immediately, so that it's a honeypot password or something like that. I forget what it's called, but there are systems like that so to protect yourself, right, from like if you're arrested or something like that, right? All right, so you still need to keep track of the size of an array, right? Again, in general, there is no way to determine the size of an array, right? Certainly never for a dynamic array. Right? Certainly never for a dynamic array. There we go. And that was the code that I had up here first, because I think somebody asked yesterday, well, what about using size of to determine the size of an array? And so, yeah, go ahead.
Could you do size of array divided by like size of one of those members?
That's what I'm about to show you here. So, size of one of the members.
Or like
Only if the type has not been erased. Okay, so I'll show you what I mean here in a second. So I've got a static array of size 10. I've got int n size 15. I've got another static array of size 20. And I've got an uninitialized pointer here. And then an initialized pointer to an array of size 30. And then I create another array here using this variable argument here. These are called VLAs, variable length arrays. Right? It's basically a static array, but using a variable instead. Right? And then I try to print out the size of each one of these. Let's see what it looks like. Right? So let's walk through this. N is 15 because that's what I set it to. Okay? I'm just printing out the value stored in n, not the size of n, not the number of bytes of n, but you can do that. In fact, let's do that, since you just asked for that. Let's go ahead and go with size of n, and that should come back as 4 because it does know that it's an integer, right? And then LD, of course. Right, there we go. Right, there we go. 4 bytes in an integer. Now, we didn't put in int here, right? What it did is the compiler went over to this thing and said, oh, I know what it's declared, and it's int. But if I had done something like this, and you can do something like this, right? A void pointer of some sort, right? It's not going to know what is stored in there because the type has been erased, right? Let's go ahead and restore that back to n. And then 40, where did we derive this 40 here for size of A? It's of size 10, and again, the compiler goes back and says, whoa, this is an integer, so 4 times 10, that's 40 bytes right there. I know that because the compiler knows that. It did that at compile time, right? In fact, these are macros, right? They are a copy replace, right? It's done by the preprocessor. Then for B, we had 80 because it was of size 20 times 4. What about this one, 8? D. What was D again? D was just a pointer, right? It's not going to tell you that it was 30 times 4, 120. It's going to tell you the size of the pointer itself. There are 8 bytes to a pointer in this system, okay? And then finally, E sub n, it is able to derive that it is 60. How? Well, it's able to go up to n and say, okay, that's 15. So you wanted 15 integers times 4, then that gives me 60. Right?
What if you did the size of and
Yeah, well, I think he was size of what?
and d? What's the
What, and D? Or,
where you get the value in the array?
oh, okay, like
Like do an array?
like what, ace of 0? Like that? Or, that'll probably give me 4.
I'm probably saying no.
Yeah, because there are 4 bytes to an integer. And so I think that this is the trick that he was talking about, where, okay, well, if you can get that, all you need to do is divide out by 4, or more interoperably, size of int, because you know that there are integers in there, right? All right, GCC, and there. Now you do get 15. You can recover this, but this is all done before it's compiled. Why are you doing this, right? You know how big it is because you made it into a fixed size static array, right? So you're doing bookkeeping, but with extra steps, right? Yeah.
Would it make more sense to do the bookkeeping with the struct? So you have like one type that has the length.
Yeah, you can do something like that. You could, in fact, that's a lot of people do that with strings to keep track of the length of the string, so they don't have to keep calling strlen. We'll get to that later. We haven't gotten to structs yet, so don't worry about it. But yeah, you can. That's a trick that you can use. And it's a common trick. I don't want to say it's a hack because it's not a hack, but that is a common trick. We haven't gotten to structures yet, so I don't want to do it yet. Right? Okay. So you can do it circuitously for static arrays, but that's because you are letting the preprocessor do your work for you, and you're doing extra steps in your code to do all that bookkeeping. In general, it's just going to be easier to keep track of it in a variable, right? Just keep track of the size of an array in a variable, right? This is the easiest. Right? There are other functions. For example, calloc and realloc. Calloc will do the same thing. It'll allocate some memory for you, but it'll also zero it out. I forget why it's called C. I think maybe it's just C allocation. I don't know. And then realloc will actually expand or contract the amount of memory that you want given a pre-allocated memory. So if you've got 5,000 integers here and then you need a couple thousand more, you can reallocate it. Of course, if it runs into memory that doesn't belong to you, then it'll fail and return null, and that's why I don't really cover them. But if you want to use them, fine. If you want to read more about them, RTM. Right? What does RTM stand for? Read the manual. Or you can emphasize that by saying RTFM, which is freaking. Yeah.
So realloc extends the memory you want,
Yep.
but if you want to have memory in a different place, you have to use malloc.
Then you have to use malloc. Yep. A completely different and you really have, unless you're going under the hood of malloc and writing your own malloc and doing syscalls to get specific, like to change the behavior of how malloc works, then you really it's all opaque to you. You don't have to worry about how it's doing it.
There's not really a reason to use realloc.
If you want to use it maybe as a buffer, like you're reading in a file and you don't know how big it's going to be a priori up front, and so you allocate this space and then it ends up being larger, so realloc, right? That means that you don't have to do a copy of all this stuff into a new space, but eventually you probably will hit something that is being used, in which case then you have to do a malloc anyway, right?
In case you're wondering,
Yeah.
where does it care that I went past the array size?
Yep, exactly. Is it Cygwin or is it some native Windows thing?
Native Windows.
Okay, all right. Exactly. All right, so memory management. I previewed this last time. Once you allocate a chunk of memory, of dynamic memory, I should say, you can use it however long you want in your program. Right. And somebody did ask on Monday, does it get cleaned up anyway? Yeah, the operating system will reclaim all the resources, yes. But once you are done with it, you should clean it up. Right? You can free up memory, right? In other words, give it back to the heap or to the OS, whichever the case may be. The operating system might just say, okay, I'll just go ahead and put that back on the heap, and if you ask for more memory, I'll go ahead and give it back to you. Or I could go ahead and give it back to the operating system, and the operating system, well, that process over there needs some more memory, so I'll go ahead and reallocate it over there, right? That's an operating system thing. Unless you're doing operating system programming, then you don't have to worry about it. But you can free up memory using the free function, right? You simply pass in the pointer to the dynamically allocated memory. Now, you might be wondering at this point, wait a second, you said that you have to do your own bookkeeping. You have to remember that there are 100 integers in that array so that you know exactly how big the size is so that you can, say, free it up. The operating system knows, right, because it's the one that allocated it, but it's not going to tell you. There is no syscall that I've ever found, interoperable, POSIX compliant, or even Windows, that will tell you exactly how big it is, right? The operating system does keep track of it somewhere. It's just that it's not going to let you know what it is. The operating system doesn't know how to, doesn't need to be told, you need to free up those 40 bytes over there, or you need to free up those 1,000 bytes over there. It'll just say, free up those bytes that you allocated. Okay, will do, right? It takes care of it. So for example, let's go back over here. Oh no, oops, that's not what I wanted. So undo, 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 all the way back to what I had before. Come on, I shouldn't have gotten rid of it. There we go. All right, let's get rid of all of this. Actually, not all of it. Let's get rid of that stuff. All right, so we are allocating this. After I'm done with it, I simply just free the array, okay? Because I'm done using it. Now, I'm about to exit out of the program anyway. So you do have an argument here that if the memory if the memory's lifespan is intended to go all the way to the end of the program, fine, you don't have to free it. But then you get into bad habits. Then you get into bad habits of not freeing stuff. By explicitly freeing it here, even though you don't have to, you stay in those good habits. Whenever you're done with it, free it up. Right? Well, let's see how this works. Right? First 42, last 101. It frees the memory up, and then it stops the program. I did this explicitly to show you what happens when you don't play nice with it. ARR sub 0 is equal to 1,000 now. And we'll print it out again. I've freed it up. So should I be able to access it again?
It should give you the segmentation.
Okay, yeah, something like that, right? In fact, oh wow, okay, it's not doing well behaved here. Let's try a larger one. Let's try a much larger array. 1 million. There we go. All right, and I don't have to change anything. Now this should be getting, there we go, finally. So it was doing that trick of, okay, fine, it's just a small amount of memory. I gave you this big amount of memory, freed it up, who cares, right? But now because I'm going into multiple pages, now it cares about, this kind of stuff. And so it does segfault because you freed it up, all right? Possibly it even gave it to another process. That is possible. And it doesn't even belong to me anymore, so attempts to access it after it's been freed are undefined behavior, segmentation fault. Right? Okay, so do not access the freed memory. Right? Dot, dot, dot. It is undefined behavior. Could be a seg fault. Okay, fine. I won't do that. What if I get really overzealous here? And what if I free it twice? Segmentation fault. Right? In fact, you might sometimes get a message that says double free fault, right? That you tried to free something, then you freed it again, right? So you do have to be careful here. Don't free multiple things, right? So, or don't free multiple times, I should say, right? Because you already gave it back to the system, the operating system. The operating system says you can't free something that doesn't belong to you, seg fault, right? All right, so don't do that. Don't do that. And another thing that you don't do is free uninitialized pointers. So what I'll do here, I've freed it up, so array is equal to null. Right? Can you free a null pointer? Can you free nothing? Right? Apparently you can, but again, it's probably undefined behavior. Who should be coming out of the screen right now and smacking you in the head? That guy, that wrestler, Bret Hart, right? Don't dereference a null pointer, right? All right, so those are some little gotchas there, okay?
Free up something that you could find on stack.
Yeah. Okay. So let's go ahead and create, I don't know, int x is equal to 42, int ptr2x is equal to x, right? And then we'll try to free x, but it has to be a pointer here, right? And let's go ahead and get rid of that.
Would you free the pointer?
Yeah, it's, oh, sorry. Yes, that's what it's complaining about there. 2x. There we go. Segmentation fault. You can't give back your stack, right? Not only are you, here's your stack, not only are you smashing it, you're saying, I'm going to go ahead and give my stack back to the operating system. You can't do that until a program is done executing, right? So, a list of things, don'ts. Don't.
What does that try to like free up the whole stack space of your program?
The whole page.
Wherever it points to. So if you're pointing to the middle of the stack, you're trying to shove out that one dish, and it's all going to fall. Yeah.
So, since there's a lot of dumb things you do to memory that can be picked up on, you talked about programs to like static analyzers. Are there any that like run as you're typing?
As you're typing?
Yeah.
No, not really. I mean, if you have a more sophisticated IDE than we have right here, it'll do basic syntax errors. So for example, if we were doing Java in Eclipse or something, you start typing and it's compiling in the background every second, or trying to. And so if you misspell something, you immediately know it, and it underlines it with a red mark. But static analysis, you could program a static analyzer to always run in the background, and then similarly have that squiggly red line under there. But that's the extent of it.
It doesn't do things like if you dereference null pointer, it's not gonna.
So that's where Valgrind will come in. Dynamic analysis, when it's running. Right? So for example, let me go ahead and clean this up. I don't know. Let's do one of the things that we weren't supposed to do. Nope. Yeah, okay. Yeah, we'll go ahead and keep that. Oh, please tell me that you have Valgrind. Which Valgrind? Excellent. Okay. So GCC. I'm going to give this a G flag. The G flag, what that does is it says compile this for GNU debugging. In other words, retain the variable names, retain the function names, retain the line numbers, because I want some information about this, right? If you don't, then all that metadata is lost, because ultimately your running program doesn't care that you named it X, right, or Y or something. So I'm going to go ahead and compile this for debugging, and I will run it through Valgrind and a.out. And I'm going to get a report back after this is done on everything that potentially went wrong. Right? So for example, invalid free, right? Where? At demo.c line 11. Why was it invalid? Because, and it might get, if you reconfigure this to give you more information, it'll probably give you more of an explanation of why it's invalid. Right? Memory leaks. Right? So let's go ahead and go with int arr is equal to int star malloc of n times size of int. And I'll never free it up. I could free array, but let's say that I don't. I am not a good manager of my own memory, and so I'm ultimately going to lose how many bytes here am I going to are going to be lost? Lost as in leaked. 1 million times 4, that's 40 million bytes, or 4 million bytes, excuse me. Right, so GCC, run it through Valgrind again, and I get 2 errors in 2 contexts here. Definitely lost 4 million bytes in one block, because I never freed that up. Right? So this is going to be used for, later on when we start detecting memory leaks. Not this week, but in next week's lab when you do work with arrays. You'll run Valgrind, you'll see that what's happening, and then fix what's happening, run Valgrind again to verify that it's fixed. Right? But that's a dynamic analysis tool, and you use it when you actually run the program. Right? Okay? Good questions, but you're getting ahead. All right, so don't double free. an array, right? You cannot free something twice, right? Don't free your stack, right? Don't free null or invalid variables, right? What else did we do that we shouldn't have done? I forget. Don't try to use an array after it has been freed, right? And finally, always remember, always remember to free your memory when you are done with it. Failure to do so will lead to memory leaks. We talked about this on Monday, but what happens if you've got a long, again, if your program only runs for like 2 seconds, who cares? But if your program is intended as a long-running program, like a server or a web browser or something like that, where a user is sitting there with the program open hours at a time, and you are claiming memory, you're claiming chunk of memory after chunk of memory after chunk of memory, right? You are eventually going to run out of that memory, right? Or you're just going to waste system resources doing nothing with it, and then everything gets slowed down, right? Yeah.
Isn't there also security issues with having memory leaks?
You can, if eventually it dies and it doesn't die well, then it could lead to a buffer overflow, maybe. Most attack vectors like that are through buffer overflows, though, and gaining access to memory that doesn't belong to you. The last major one that I remember was Heartbleed, where you could send a bad packet request to a web server, and because of a failure to check for buffer overflows, it would send back. It could potentially send back raw memory memory contents, and then if you got lucky, right, you did this over and over and over again to try to trigger it, and then of course maybe you got garbage, maybe you just got part of an image or something like that from the web server, but maybe you get a chunk that looks like an SSL key, right, and now you can start SSL key farming, where you're grabbing all of their secret keys. Once you've got their secret keys, it doesn't matter how much encryption they have, you've broken it. That was a Heartbleed, maybe 6 years ago, 7 years ago, I forget.
Severe.
Yep, Heartbleed attack. We're gonna get Heartbleed bug. There we go. How does it work, et cetera, et cetera. Right. And I forget why it was called Heartbleed, but whatever. They came up with a cool sounding name. Say what? Yeah, I don't know, some metaphor like that. They had to make it sound cool, right? Because otherwise, doing security research like that is kind of boring, and so you have to, let's jazz it up with a cool name there, right? So if you have to do memory management, a good question is, who owns memory? Right? In other words, which function is responsible, which function or functions are responsible for cleaning up after memory, right? Or cleaning up the memory, right? And it's all, I mean, there isn't like a hard rule that I can give you, right? That it's always this function, and it's always that function, or something like that. Because again, even if you're at the end of a program, right? Who cares about freeing it up? Again, get in that good habit of doing so. But if you allocate memory in a function and then you're done using it in that function, that's where you deallocate it. That's where you free it up, okay? So for example, let's go ahead and create a function up here, int foo, or do something complicated, right? And within that, we go ahead and allocate some working space, right? Say 1 million integers in here, okay? And I'm just copying this over, and we're going to do something with those integers, right? ... And then I return, say, 0, because it returned fine, right? So again, I'm not, I don't want to get into what I'm going to do with those integers. I'm just declaring enough space here to work with 1 million integers, and then once I'm done, I return, right? Now let's go down here to the main and call that function. Do something complicated. Is that what I called it? Yeah, complicated. Right? All right, GCC. And it's not going to manifest itself here because, of course, I'm just wasting 4 million bytes or whatever it was, right? But if I run it through valgrind, again, I see that message that I definitely lost 4 million bytes. Where was it originally allocated? In do something complicated on line 8, right? Right there. And then it was never deallocated. It was never freed. So over here in main, can I free it? Maybe? Yeah, well, what? I need to give it something, right?
Or no, you can't.
I can't. Why? Because it's a local variable that is scoped to that function. Right? So how could I possibly get access to that variable? Right? Now, I could go with another solution here that I'm going to tell you not to do immediately because, but I'm going to show you what I'm talking about here. What if I did something like this, int ARR? And then I said, okay, go ahead, ARR there. And now I can go ahead and free ARR down here. This will compile. Right? That's called a global variable. And I've never shown this in class, but some people are submitting stuff that uses global variables. So I don't know where you picked it up, but do not do it. In fact, there's not a meme, but there is an old saying that globals are evil, right? Just do a Google search for globals are evil, and you will see a million different reasons why you do not want global variables almost ever, right? Basically, you want to limit the scope of variables as much as possible. As much as you would for like a for loop, right? You can go int I and then for I equals 0, blah, 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 or whatever, right? But it is much better to use the more modern case, or modern convention of for int I equals 0, ... Why? Because that scopes I down to that for loop and that for loop only. You limit the scope of variables as much as possible because you don't want chaos in your code. This is about as terrible as it can get with respect to chaos, right? This is a global variable. Any piece of code can see this variable. Any piece of code can screw this variable up. Any piece of code can do whatever they want to that variable, right? Absolute chaos. Generally, you do not want to do that. Right? So let's go back over here and do it correctly, int ARR. So the question is, who is responsible for cleaning up that memory? Well, main is not responsible for cleaning up that memory because it doesn't even know that do something complicated is allocating that memory. Do something complicated is allocating that memory. So, therefore, it is responsible, right? Do something complicated is responsible. So, ... Before we return, we should free the array. Okay? Another example. What if we have a function that is intended to return an array? What would that look like? So for example, let's go ahead and document this function. This function creates a new dynamic array of the given size of integers, a new dynamic integer array of the given size, and initializes each value to 1. Right? So I'm going to call this get_ones array, right? Because that's what it does. Okay? What should the signature of this function look like? If it's going to return an integer array, what does that look like? What is an integer array? Int star, exactly. Right? And if I'm going to take the size, I want 10 ones. I want 20 ones. I'm just going to go ahead and take it int n. So let's go ahead and implement this function now. Right? So the first thing I do is create an integer array. I'll just call it result, right? Int star. Call it to malloc, n times size of int. And I'll immediately return that result. Is it filled with ones yet? No. What's it filled with? Who knows? Dead beef, garbage, right? Whatever was there before, undefined. So let's go ahead and define it by going through, starting at the first one, I is less than n, I++, and this is the idiomatic for loop for arrays, and set result equal to 1. Say what? Oh, sorry, results of I. Yep, thank you. Keep me on my toes. Right. It still compiles, great. All right, so let's go ahead and take care of it, or use it now, right? Int star ones is equal to get ones array, and I'll get a ones array of 100 ones, right? I don't care about it. We can print it out if you want to. We can add them up if you want to. Do something less complicated with them if you want to. But who's responsible in this context for cleaning up this memory now? Is ones array allocates that memory. Should it free up that memory before it returns it? It can, but yeah, you ask. I'm the function now, right? You asked me for an integer array, and I'm going to give it back to you, full of 100 ones. I created this integer array with 100 ones, and then I immediately threw it in the garbage. Can I give it back to you? No. Right? In fact, hopefully this will be a seg fault. Oh, actually, I'm not doing anything with it, so let's do something with it. Printf middle is equal to %d and the line ones of, I don't know, 40, somewhere in the middle. Okay, we're good. OBS is dropping a few frames, but not a lot. All right, well, great, it got, but now let's kick it up. 1, 2, 3, 1 million arrays, and then, I don't know, 40,000, somewhere in there. Ah, come on, 40,000, 1,500,000, somewhere over there. Nope, all right, fine. 999,999, the last one. All right, it should be seg fault. Say what? Why? It's not. Well, I mean, it's free. I freed it up though, right? I freed it up. So unfortunately, I'm not getting it to. I'm not forcing. I think I can force it with R dynamic. R dynamic. Oh, okay. Oh, I misspelled it. Dynamic. There we go. Now fail, please. Come on. No, okay. I couldn't force it. All right. Anyway, it's letting me do this, but it should not be letting me do this. But it is still undefined behavior. Should get ones array, should it return? Should it free it up, throw it in the garbage before it gives it back to you? No. So in this context, who is responsible for cleaning up that memory? Main, exactly. And here it would be ones, because that function gave ownership over to main. Right? Now main owns that memory. If main were to give it over to another function and ownership transfers to that other function, then that function is responsible for either transferring ownership or taking care of the memory for you, right, by freeing it up. It's all a matter of design, right? You ask yourself, who owns this memory? How is it transferred? Where should it be freed? It should not be freed before you're done using it, right? So again, there's no hard and fast rule that I can give you. It's only you thinking about your design and thinking it through and getting it to work. And then making sure it doesn't crash, and then running valgrind on it to make sure that it's not leaking anything. In fact, I think that we can run valgrind on this and it will not, it'll say no leaks probably. Come on, where's valgrind? There we go. All right, yep. All heap blocks were freed, no leaks are possible. Excellent. Then valgrind will definitely complain about that. Free result. There we go. GCC. 2 errors detected in 2 contexts. What are they? Free, double free here. Invalid free. On what line? Line 35, which is right there. Right. Valgrind is a wonderful tool. Right. And by the way, we'll demo it more fully next week. But if you are looking at those kind of tools, if you go to the repository and go to documents and you go to this troubleshooting guide, where is it? Troubleshooting guide. First of all, your first line of defense is testing. Now that you've done some some informal unit testing, this Friday you'll be doing more formal unit testing. That's your first line of defense against bad code. Your second line of defense is to use a linter. Always use the WAL flag. Take care of all warnings because those are probably, will probably manifest themselves as bugs. Use a static analyzer. Clang is another compiler that allows you to turn on warnings if you want to use it instead. In fact, you can use it as a full static analyzer by using clang, analyze, and then your code before you even compile it. So for example, clang, analyze, demo.c. All right, it didn't find anything. Right? It's not super sophisticated, but you can also use clang as a static analyzer tool by scanning the build. The entire build process, it's much more intensive. We can take a look at what it looks like. Scan build GC, oh, it might not have scan build there. Build GCC demo.c. Nope. You'll have it on CS50 IDE because I requested it to be installed. Or you can do even more sophisticated tools, like for example, Facebook has this static analyzer tool called Infer. It's multi-language. You can go ahead and download it and install it and play around with it if you want. These are all static analysis tools that you can infer certain bad things. I've used it mostly with Java, but even then, I've never found it to be all that sophisticated. It only finds stuff that is pretty obvious to anybody who's done Java for 2 years, 3 years, or something like that. But there are even more sophisticated commercial solutions. You can send your code out to companies that will do static analysis for you, and they'll charge $50,000, $100,000 for their services, and supposedly their tools are even more sophisticated than this. But don't send your hello world out to and spend $50,000 on that, right? Otherwise, dynamic analyzer, the Valgrind here, that we'll demo that more fully later on. And then finally, the best thing is a full debugger, right? And GNU GDB is the debugger that I'll show you next week, right? You'll have a full hack on it where you'll use GDB to debug a tic-tac-toe program, right? And so you're going to go on a bug hunt. Perf testing is a little bit different. We'll look at that at the end of the semester. It's performance testing, so it's not looking for bugs or issues with your programs. You're looking for performance gains. Where is your program? Your program is slow. Where is it spending most of its time? Well, it's spending most of its time over there in that function. 90% of its time, it's in that function. Look to optimize that function. Look to see, is there something wrong or inefficient in that function that I'm doing, right? Okay, so that was a little bit of a detour, but that's fine, right? So who owns the code? Whatever piece of code owns the memory is responsible for cleaning it up, right? The two examples that I gave you, if the function only allocates memory for temporary use, does not return it, it is responsible for cleaning it up. It owns it and it must free it, or you'll have a memory leak. If the function returns an array, then the calling function owns it and it's responsible for cleaning it up. Okay. I'll make sure that you have this code in the notes. So C. There we go. By the way, all of this stuff is really only an artifact of C, C++. Most modern programming languages will not have memory management at all. Java, C#, Python, etc. Most interpreted languages will not let you, will discourage you or will not even let you do manual memory management because they don't have pointers. This is systems level programming, so you're taking on a greater responsibility because, what is the Spider-Man saying? With great power comes great responsibility. You have much greater power. The performance of C, the performance of Java will never match the performance of C. The performance of Python certainly will never even match the performance of Java, which will never match the performance of C, right? So you're basically that lack of memory management, right? That freedom from that responsibility, that comes at a huge cost, and the cost is performance. And of course, systems programming. If you want to do systems programming, C, C++, those are the only games in town. Rust with an asterisk on it. Have you heard of Rust? Okay. The folks that created Rust wanted to create a safer programming language. They just succeeded in creating a much more complicated programming language that still nobody uses. I don't know. Maybe more people are using Rust now.
Like as a C alternative?
Yeah, for systems level programming for Rust. Rust. Oh, okay. Actually, I'll comment on it. I will. Bad. There we go. I'll leave it in there, and so that you remember that it's bad. All right, Rust programming, not language, not the actual Rust. Oxidization. There we go. Rust programming language. There we go. Well, again, there are only two difficult things in computer science. Right? One of them is naming things. So why a language empowering everybody to build reliable and efficient software? Get started. Show us what a hello world looks like. Oh, whatever. Anyway, you can check it out. Say what?
You go to the Rust that you just on the homepage, and then go to Playground, I believe it has a demo right there.
All right. There's a playground. Oh, there's a
Yeah,
playground.
so you can just run it in your browser.
There you go. FN stands for function. Print ln, going to print the line, and hello world there. I've not used it in any meaningful way, so I'm not going to be able to show you any Rust magic here. But there you go. All right. So, yeah, we've got 15 minutes left. In fact, we already previewed it. Using arrays and functions. Right? So if you're going to pass an array to a function, what else do you have to pass to it in order for it to do bookkeeping? And the size of the array, right? All arrays are simply pointers, so you just simply pass a pointer in. To pass an array to a function, you pass a pointer. And in addition, you have to pass the size of the array. In addition, you must pass the size of an array to the function. If you don't know how big it is. So let's go over here and play around with another example. I'm going to sums up the elements in the given integer array. Right. Pretty simple. What should I call this? Sum. Right. Even though it's programming, and even though a compiler doesn't care if you spell things correctly, you should still spell things correctly, because code is written not for computers, but for other people to read and understand. Right. So, I will return an integer because that will be this, the adding them all up. Right? I will take an integer array, and to do that, it's just simply an integer pointer. What else do I need to pass to the function? The size of the array. Right? So int total for int I equals 0, I is less than n, I plus plus, printf, or not printf, total is equal to total plus a sub, or race of I, right, there we go. And I'll return total. One problem and one optimization. What are they? What's the one problem, first of all? Hint, line 11. What value is in total as of line 11?
None.
Undefined, so I should initialize it to 0. Why? Because garbage plus 1 is garbage. Garbage plus 2 is garbage. Garbage plus 3 is garbage, right? Optimization. Do I have to rewrite total?
Nope.
Plus equals array. Okay. So let's come down here and let me give myself a really quick test case here. Int primes 2, 3, 5, 7, 11, 13. How many is that? 6?
Yep.
Int n is equal to 6. And so int sum is equal to sum of primes n. Strictly speaking, that's going to be compilable code. It is going to run. Is it a good idea to name a variable after a function?
Probably not.
Probably not, right? And the reason being, let's see, square root. Let's see if this compiles. All warnings, you be quiet. I can get you to compile. There we go. I shut off all warnings, right? So I did exactly the opposite of what I've been telling you to do this entire time. right? In other words, it compiled and it worked. Does that look right to anybody? No. This is a preview of something that we're going to look at much, much later on. You have pointers to variables. A pointer is just a memory address. What else is stored in memory? Everything is stored in memory. Functions are stored in memory. So what I'm doing here is I'm taking the memory address of the square root function, I'm treating that as an integer, and then I'm putting that into sum. Right? You can get really confused if you use the same name as a variable and as the function. Don't do that.
So if you had a variable named sum in the same scope as the function sum, could you even point to that?
Then you've got a recursive function. A meta-programmed recursive function that changes its own code at runtime.
That sounds disappointing.
Some? There, now I'm doing it. Because it can disambiguate. If you declare it like this, then it knows, okay, you mean a variable. Right? I know what you mean. Right? But if you do it like this, then I'm saying, my function now points over there. That's okay. I'm going to go ahead and continue operating here. I'm going to go ahead and add everything up, return the total, but the next time you call this sum function, you're calling the 0 memory address. Something like that. Right? Hopefully it's not that simple. All right, so I'm going to go ahead and go with total and printf %d and line. And total. So somebody do that really quick in their head. Oops. Oh, and then the, I shouldn't have, I need to roll that back. There we go. What's the sum of the first 6 primes? No? All right.
24.
Sum of first 6 primes. Let's see if you're right. 41. Oh well. 41, excellent. We got it. All right. So, what I did is I passed in the array, but I also had to pass in the size. If I didn't pass in the size, how the hell am I going to know how big the array is to iterate over it, right? There are no tricks here at all because you cannot pass. I mean, you can pass, in some sense, a static array, but it ain't going to know that it's static once it gets to that function, right? All right, yeah. Oh, question?
Yeah, so just kind of about memory management in general. So like when we would program for like a lab or a hack, is there a situation in which we would want to allocate memory, or is
Oh yeah, next week you'll be.
so is that like something you do when it gets big enough? Is it just like best practice to do that?
Oh yeah, okay, so when do you want to use static arrays is probably the question.
Yes.
And if it's small, if it's fixed, then go ahead and do it. For example, later on we might look at an example where I create a character array of name, or I don't know, years, something like this, where I allocate it to freshman, none, sophomore, senior. Oh, I skipped junior. Sorry. There we go. So if there are only 4 things, and there are only ever going to be 4 things, and you're never going to change that ever again, then yeah. Now, what you would have to do here is I think you'd have to specify at least one of those sizes. That's big enough. There we go. We're not into strings yet, but here's a use case where you would do this, right? But if you are never going to change it, then there's this magic keyword that is actually what I was going to talk about next. So I'm segueing back in. Const. What do you think const stands for? Constant, exactly. And if something is a constant, then it is not a variable, right? So for example, let's come back over here to my sum function, and I'll go ahead and add it up for you, but also, I'm going to go ahead and change it. I'll zero it out. Right? Did you expect that when you called the sum function? Right? Here's my array. Please sum it up for me. Also, go ahead and change them all to zeros, right? Delete my data. Right? Did I really mean to ask them to do that? No. But that's exactly what I was able to do, right? I'll go ahead and call it again, and then print out the total. And the second time that we go through it, it's all going to be zeros, right? So I corrupted, not only did I did what you asked, I summed up all your variables, but I also screwed up your data. Right? I don't want you to do that. So I'm going to go ahead and slap a const in front of this. Right? Now that doesn't make this array constant. It makes it only read only for this function right here. And now when I try to compile this, the compiler is dumb, but it is able to figure out, hey, you said that that was constant. You cannot change it. So compiler error, I'm not going to do that. Right? You need to get rid of that line right there because you're changing it. Once you do that, then everything is fine. You can't change it, right? So you get the same answer every single time. Rule of thumb is if you pass in an array and you are going to change it, then you don't make it const. You can't make it const, right? But if you are going to pass in an array and you're going to make the promise, right? Scout's honor, right? To not change your array, right? Then put a const in front of it. Right? Now there are ways around that, so it is just a promise, right? You can do an indirect variable that then points to that other thing, and then you can go ahead and muck with it all you want. And the compiler is not going to be sophisticated enough to detect that. That's why it's just a design promise, right? You can do underhanded C all you want. Underhanded C contest. In fact, there's a contest for it. Contest. Underhanded C contest. It's an annual contest where you can submit a program that is completely C compliant. That I think it's actually cheating if you exploit a compiler bug, or maybe they've got a special category for it. But basically, it's an underhanded C program that looks innocuous, but then actually does something nefarious, right? And it's through obfuscation, basically, right? I don't know. What's an example? An overview of NAND poisoning attacks. 0 by 0 is NAND, whatever, right? So parse the remaining elements. You can look at your own examples later on, but you can write underhanded C, and it's a contest, the annual contest for it. But you only do that for contests, or if you're trying to undermine a Russian system, right? Okay. So we'll pick it up there on Monday then.